So I wanted to do one of the most famous problems in probability to start with, and then we'll go back into the non-naive definition. At the very end of last time, we started the non-naive definition, so we'll get back to that in a little bit. But first, this is a problem that everyone who studies probability should be familiar with. That's called the birthday problem. It's a very natural problem. Some of you have seen it, I'm sure, but it's very, very surprising to most people the first time that they see this result. And I wanted to talk about how to think about, even if you've seen it before, I wanted to talk more about how to think about the problem. So the birthday problem is very simple to state. The problem is just you have a group of people at a party or something, and you want to know how likely is it that two people have the same birthday. Maybe three people will have the same birthday. Maybe there are several pairs that have the same birthday. But how likely is it that you can find at least one pair of people who share the same birthday? Because if it's a large party, then no one would be surprised. But if there's a small number of people, most people would think that's a pretty big coincidence, right? Okay, so we want to know, for example, we might want to ask, how many people do you need in order to have at least a 50-50 chance that two people have the same birthday? We want to answer questions like that. Okay, so that's called the birthday problem. So just to state it in general, let's say we have k people, and we want to find the probability that two have the same birthday. Not a specific two, of course, but that in that group, that you can find two with the same birthday. Well, we need to make a few assumptions about birthdays before we can actually solve this. Was anyone here in this room born on a February 29th? Okay. You were? Yeah. Okay. Well, will you be offended if I exclude February 29th? Okay. So we have permission to exclude February 29th. It's a hassle. We can do this problem dealing with leap years if we really want, but it's a hassle. February 29th is less likely than any other day, so I don't want to treat it as 366 days in a year. But we want to use 365. It's not going to make that much of a difference. It's pretty rare. We have a large enough class, at this point, you know how to compute the probability that at least one person in this room has February 29th. Well, now we know the probability is 1, but before that, we didn't know. You can compute that probability if you knew how many people are here. It's a large class. Okay, well, anyway, but I got permission to exclude February 29th, so we're going to assume there's 365 days in a year, just for simplicity. And we're going to assume that the other 365 days are equally likely. So, that seems like a plausible assumption. It sounds plausible to assume the other 365 days are equally likely. That's an empirical question, not a mathematical question, is that true or not? If you look at data on this, it's actually not exactly true. There are seasonal effects, which kind of strangely differ in different countries have different seasonal effects. There are more babies born 9 months after a holiday, and you can try to figure out why. Not a huge difference, but there are some small differences. But anyway, we're going to assume they're equally likely, okay? And we're also going to assume independence. Later, we're going to talk more about the formal definition of independence. I'm going to say independence of births. Later, we'll talk more about the formal definition of independence, but right now I just mean that in an intuitive sense. Like, for example, if we knew that in this group of k people, if we knew that we had twins, then that's going to change things, right? We assume that one person's birthday has no effect on anyone else's birthday. So using the word independent kind of in an intuitive way here. Okay, those are our assumptions. And now we want to find the probability. Well, a lot of the challenge of this course is just recognizing pattern and structure, right? And this problem, sounds like something we haven't done, but it should start reminding you of some of the homework stuff, right? The courses, the robberies. This is pretty similar to the robberies problem, just a different application, different setting, but it has a similar structure. So So therefore, you're all kind of experts at this kind of problem now, and I can do it pretty quickly. Okay, so first of all, if k is greater than 365, then the probability is 1. Because to visualize that, we can think of this as like a balls in boxes kind of thing. But like, remember I was talking last time about labeling? We should think of these people as labeled from 1 to k. We're not going to treat people as indistinguishable particles, right? They're people, they have individuality, okay? So if I want to draw a picture, I'm going to draw 365 boxes, but I'll put a dot, 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 so I don't actually have to draw 365 boxes. This is the January 1st box, or bucket, or whatever you want to call it. This is the January 2nd one. This is this December 31st. So imagine I had these 365 boxes, and then each person, I'm assuming that the people are labeled, but I'm just going to put dots for now. So this would be the case where three people are born on January 1st, 1 on January 2nd, 2 on December 31st, and however many are in between there. So we'd imagine a situation like this. Okay. Now, if you have more than 365 people, but you only have 365 boxes, then clearly there must be a box with more than one dot in it, right? Does that seem like intuitively obvious? There's more people than boxes in that case. That's called the Pigeonhole Principle in math. It's a very simple fact, right? If you have more dots than boxes, then you have to have a box with multiple dots. But it's a useful principle, simple but useful. And okay, so that's the answer when k is greater than 365. And I also wanted to mention, by the way, that this kind of problem is extremely important in computer science. Because often you have problems where you have clever ways of storing information in different data structures, and problems happen when two things try to store them in the same way. That's called a collision, and you want to know what's the probability that you're going to have collisions like that. So it's a fun problem to talk about, but it also has a lot of applications in CS and engineering and elsewhere. Okay, well that was an easy problem if k is greater than 365, but now let's do k less than or equal to 365. Now, I've asked a lot of people, over the years, I've asked a lot of people who have never seen this problem to just to guess intuitively, how many people would you need in order to have a 50-50 chance that there is a birthday match? And a typical guess is like 150 or 180, maybe take 365 divided by 2 or something. Some are definitely well over 100. Almost everyone I've ever asked this question to, if they hadn't seen it before, says something over 100. Okay. So that's the intuition of almost everyone on this before they've studied it. The answer is 23. So that says if you have 23 people, so that's not, here we have hundreds in this room. We just take a couple rows here. I'm not going to spend 20 minutes surveying all your birthdays, but if we just took a few rows here, it's extremely likely that there's going to be a birthday match. So we want to just see mathematically, first of all, we want to see mathematically how do you compute that? And then secondly, what's the intuition? How could it be 23 when there are 365 days in a year, but if you have 23 people, which is a small fraction of 365, why is it already 50-50? It's slightly over 50-50. I think it's like 50.7% chance if you have 23 people. Okay, so let's find the probability of a match. Now, it's a little bit easier to work with the complement first, so let's find the probability of no match. Then we can always do 1 minus that to get the probability that there's at least one match, okay? So that's often a useful strategy. You want to think about, is it easier to find the probability of the event or the complement of the event? In this case, it's easier to do the complement. Okay, now this is really similar to homework, so I'll just do this quickly. We're just going to use the naive definition of probability. That's justified because I assumed equally likely, okay? So the denominator, we immediately know the denominator is 365 to the k. It's just immediate from the multiplication rule. Numerator is just imagine the people coming into the, assume that we've given each person an ID number, and imagine that they're coming to the party one by one in order of their ID number. That's the easiest way to think about it. First person could have any birthday, that's 365. Second person could have any birthday that's not the same as the first person, so that's 364. Multiplication rule again, so this is very, very straightforward from what we've done already. The next person could be any birthday except the first two, so 363, and so on. So you just multiply. And then the only thing you have to be careful about is to make sure you have the correct number of terms here. If k equals 1, the probability of no match should be 1, because there's only one person that there's no one to match with. So this is going to be 365 minus k plus 1. It'll be really messed up if we forget the plus 1. That's another one of the most common mistakes in programming is to be off by 1 and not being careful about the number of terms. So I want to have k terms here because there are k people. So that's going to be 365 minus k plus 1. Okay, so the probability of a match is 1 minus that. So we're already done with the problem. So this was easy. I did it quickly because you've done similar stuff at this point. So if you compute well, there are ways to compute this, to approximate this in terms of an exponential, and we'll talk about some of those approximations in a later lecture. But for now, this is something obviously you wouldn't do by hand, but something you can do very easily on a computer or a calculator. And if you do the computation, what you get for the probability of a match in a few cases, well, as I mentioned, it's a little above 50%. So this is 50.7% if n equals 23, k equals 23. So that's the first case where it exceeds 50%. Now let's just look at a couple other cases. If k equals, say, 50, so a little more than double of 23, so obviously it's going to be more likely. The question, though, is how much more likely? Well, if you do the computation, you'll find that with 50 people, there's a 97% chance. So it goes way up. And 50 people, again, that's most people's intuition was that with 150 people, it's still not even going to be 50-50. This says that with only 50, not 150, it's 97% likely. And suppose that we had 100 people. Well, 100 is, a fairly large number, but it's still less than a third of 365. It's not an enormous number. With 100 people, it's 99.999 something. I'll just say greater than 99.999%. I think it's 99.9994, but maybe there's another 9 in there or something. It's at least 99.999% likely with 100 people. Okay. So that's the result of the birthday problem. But I want to, mathematically, this is basically something that's hard to argue with. And if anyone wants to argue, feel free. But your argument will be futile. This is kind of unobjectionable, but it's not that intuitive yet. Like how could this is just correct. And you've done similar problems now, but how could it get 100 people 99.999% likely? How could that be? So I want to talk a little more about the intuition. The basic intuition is that looking at k is sort of is intuitive. It's just like how many people. That's actually not the most relevant quantity here. The more relevant quantity is not k, but k choose 2. There are k people, but there are k choose 2 pairs of people. So that's the more relevant thing to be looking at. K choose 2 is k minus 1 over 2. And for example, if we do 23 choose 2, so we said that it's just above 50% if you have 23 people. 23 choose 2 is 23 times 22 divided by 2, 23 times 11. Does everyone know how to easily multiply by 11? Add the 2 and the 3 and put it in the middle, 253. Okay. So with 23 people, there are 253 pairs of people, and now it's sounding a little more plausible, I think. With 23 is a fairly small number, but 253, that's a lot of possible pairs. Any one of those pairs, they may have the same birthday, right? So now this is getting closer to the order of 365, where it seems more plausible at that point. We'll come back to later later in the course some more complicated versions of this. So this one is straightforward at this point. But suppose we asked another question. Suppose, because we're talking about coincidences, and if two people have birthdays that are one day apart, they also might find that a bit of a coincidence. It's not as surprising as having the same birthday, but it's like, oh, my birthday's the day after yours. That's, a little bit surprising. So if we ask the same question, where instead of saying they have to have the same birthday, it's the same or off by 1, then the 23 reduces to 14. And that again surprises most people, I think. With 14 people, there's a better than 50-50 chance that 2 of them have the same birthday or just 1 day apart. Now, if you want to prove that result about the 14, it's much more complicated than this. You can try to do this and say, well, this should be 363 instead of 365 or 362 or something because I'm avoiding that day and the day before and the day after. So I guess you would try to subtract 3 from that. But then it doesn't work because you're like filling in the year and you kind of have these gaps that you can't just multiply like this. That's a much harder problem, and later in the course we'll come back to ways to approximate more complicated problems like that. So the basic idea here is coincidences. There's a saying that the biggest coincidence of all would be if there were no coincidences, right? If you think of all the possible coincidences that there could ever be in the world, there's a mind-boggling number of possible coincidences, so some of them are going to happen. And what this is saying is it's only 23 people, that's 253 coincidences that could have occurred, right? So it's not at all surprising. All right, so that's the birthday problem. Oh, and I also want to mention there's a very nice applet. There's a link on the course website with like probability by surprise applets developed at Stanford that you may want to play around with later. It kind of helps to build intuition, I think, by run a little simulation, or you can either easily find birthday problem applets online. Try it for yourself. Run some little simulations and just see how the matches are coming, because it still seems, with only 23 people, but you can start to build some intuition that way. But that's one way to think of it. All right? So that's the birthday problem. So now let's come back to the non-naive definition of probability. And I'll just remind you, because we only did it quickly, and it's easy to state again. We only need 2 axioms. One, so we're defining this. Remember, we have this sample space. And we have a function p. P stands for probability. It's pretty good notation. Okay? And there are only 2 axioms. One is that probability of the empty set is 0, and the probability of the full sample space equals 1. And secondly, so this says that the empty set is an event. And if you're not yet clear on how to think of events as sets, then you really want to master that as soon as possible. The empty set is an event, but it's an event that can never occur. We give it probability 0. The full sample space is an event that always occurs. It's guaranteed. So just by convention, we say, we want for impossible events to have probability 0, and events that are certain, we want to have probability 1 by convention. Okay, and then there's only one other axiom, which is the fact that the probability of a union this could be a finite union where I go from n equals 1 up to m, say, or up to infinity, either way. I'm just going to write it this way because it's more general, but you should know that this also applies in the finite union case, equals the sum of p of a n equals 1 to infinity. And then there's a very, very important condition that this is if the a1 through a2 and so on are disjoint events. That is, they don't overlap. So that's the key condition. And this should be pretty intuitive. If you think about a Venn diagram, so this is our sample space, S. And I'm not going to try to draw infinitely many, but let's just draw 3 events. So here we have A1, A2, A3, just 3 blobs or 3 ovals. As a first intuition of probability, we can think of probability as area. Later we'll see more sophisticated ways to think about it, but that's fine for now to just think of it as area. So suppose that this rectangle it's a little too curved to be a rectangle, but it doesn't matter. Suppose that the area of this region is 1. Think of probability as area. Then all it says is that the union is this, this, and this. The area is this area plus this area plus this area. That's it. So that's what the whole thing is saying. And it says we also want to extend that to if we have infinitely many of them, but it's the same idea, okay? So that's the axiom. These are the axiom, I mean, I'll write the word axioms here, but it's just these are the two conditions that P has to satisfy. And this was a big breakthrough. I mentioned before that a big breakthrough in probability was to think of it in terms of sets and events and unions and intersections and things like that. And the other big breakthrough, mathematically speaking, was just writing down these two axioms and exploring that. Kolmogorov was a famous mathematician who's one of the people most responsible for this. Because before we just had these axioms, it was harder to say, like, what's a correct argument in probability, what's an incorrect argument. There were a lot of philosophical debates about what is the meaning of probability, and those debates continue to this day. Those debates in philosophy have continued for hundreds of years, and I think in statistics, it's important to think about these foundational issues, right? Like what does probability really mean? Okay, in the real world, it's important, but that's not the main subject for this course, and it didn't lead to as much progress as just having these rules, because basically, from a mathematical point of view, as long as you have a sample space and you have a function p satisfying this and this, and p is a function that takes events as inputs and returns a number between 0 and 1, satisfies this and this. As long as that's true, then we consider p a probability. And every theorem about probability that we do then is applicable, and we don't have to worry about what does it really mean. Okay? There are different interpretations of probability that people can debate and people can use, but as long as the interpretation satisfies this and this, then we'll be okay. So just from these two simple rules, we can derive every theorem that's ever been derived about probability. Okay, so let's start with something simple. So let's just develop some simple consequences of these axioms. All right, so let's start with something that should also be very intuitive. So I'll just call this properties. Some properties of probability that we can develop quickly from using these axioms. Okay? So the first one is very, very simple. The probability of A complement equals 1 minus the probability of A. Okay? So, we've already used this fact before because this fact is something you can see immediately in the case of the naive definition, right? Because we're looking at favorable and unfavorable. So the total number of outcomes equals favorable outcomes plus number of favorable plus number of unfavorable. Okay? But this says that this is always true, whether you're using the naive definition or not. In the picture, it should be intuitively clear, right? Because let A1 equal A complement is everything that's outside of A1, or outside of A, okay? If the total area is 1, then, if this is 0.3, that outside has to be 0.7. So that's intuitively obvious once you look at the Venn diagram. But how do we prove it? Well, the proof is very short as well. We know that 1 equals the probability of the whole space. That's axiom 1, okay? We also know that we can write S as A union A complement. S is the same thing as A, because that's everything that's inside A, that's everything that's outside A. Put those together, that's everything. Okay? Now, P of A union A complement is P of A plus P of A complement, because A and A complement are disjoint. In set notation, we would write that as just saying that their intersection is empty. There's nothing that could be in A and its complement by definition, so they're disjoint, so I'm using axiom 2. That equals that plus that, and that's the same thing we were trying to do. So the proof is just immediate for use axiom 1, use axiom 2, and we're done. Okay? All right, so that's property 1, I'm calling it. No one else calls it property 1, but it's property 1 for today. Property 2 another useful fact, if A is contained in B, so A and B are events, but this event is inside of this event. In words, we would say that what this relationship means is that if A occurs, then B occurs, okay? So this is a larger event. Then P of A is less than or equal to P of B. Again, this is obvious intuitively in terms of the Venn diagram because it says like B is like a bigger oval containing the smaller one. It has a bigger area. That's obvious from the picture, but that's not a formal proof, and we want to prove this fact. Okay, so let's just quickly prove this using the axioms. So the proof would go, well, I'm still going to draw a little picture for some intuition. Here's A, and here's B. B is this bigger thing that contains A, okay? Now, I'm going to think of B as being split into two parts. There's A, and then there's this ring of stuff that's in B that's not in A, okay? So I'm going to decompose B into two parts. So I'm going to think of B as A union with this ring. This ring is the stuff that's in B that's not in A. So I'd write that as B intersect A complement. The stuff that's in B that's not in A, okay? And this is disjoint. That is, A is disjoint from this. That's just saying that A is disjoint from this ring. So these are disjoint. So therefore, we know that P of B equals P of A. It's just immediate from axiom 2. P of B is P of A plus P of B intersect A complement. And probability, by definition, probability has to be non-negative, so you're adding something here, adding something non-negative, so this is at least P of A. So that's the end of the proof. So it's just almost immediate from the axiom 2. Question? Probability is not supposed to be negative. Well, I didn't write that. I wrote that yesterday. P is between, you can call that an axiom if you want. In that case, call this axiom 0. I stated that last time. I didn't write it again this time. The reason I didn't write it as one of the axioms is if you're writing out in full, you would say P is a function from, defined on events and taking values between 0 and 1 such that this and this. But if you want to consider that an axiom, you can. It's assumed that probability is always between 0 and 1 by assumption. Okay. So those are two simple properties. Let's do one that's a little more complicated and also very, very, very useful. And the question is, how do we get the probability of a union? Sorry, the boards are pretty squeaky. So this is property 3. How do we get the probability of a union? Now we know that if A and B are disjoint, we can just do P of A plus P of B, okay? But if you think about the Venn diagram again, here's A, here's B, and here's the intersection. Intuitively, if we want the area, what we should do is add the area of A plus the area of B, but then we've double counted the stuff in the intersection and we subtract that off again. Okay? So we're going to prove that is in fact the correct way to do it. Whether or not the Venn diagram picture is applicable or not, that's just the intuition, and then let's prove the result. And then I'll do an example of how you use this. But we'll be using this kind of thing a lot because we often want the probability of a union, and we're not necessarily so lucky as to have disjoint sets, so we want to know what happens if they're not disjoint. Okay, and the result is that we can add up the probabilities, but that we've double counted the intersection, so we subtract the probability of the intersection. Okay? So let's prove that. Well, again, let's think of it, kind of the strategy here. When you're confronted with a problem like this and you don't know how to prove it, a strategy to use would be, we know we have to somehow apply these axioms, but and axiom 2 is the most important one, but this only applies when they're disjoint, so somehow we have to make things disjoint, right? So that's the strategy. So I'm going to write P of A union B in a different way. Right here I can't apply axiom 2 because they're not disjoint, so I'm going to write it in a disjoint way. I call this disjointification, and I think I coined that word, but I don't know. So we're going to do disjointification. I'll write the word. I'll probably regret this because it's a long word. I'll try to write it fast. So we're going to do disjointification. We're going to take A union B, and we're going to try to write it disjointly. So how do we do that? Well, we take A, and then we take everything in B that we did not already have in A. So it's A union B intersect A complement, right? So that looks similar to that. The only difference is there we were assuming that A is contained in B, and here this is completely general. A and B are just any two events. Okay? So it just says we take A, and then everything in B, we need that, but we don't need the stuff that we already had from A, so we're excluding it. All right? Now this and this are disjoint, so we can immediately apply axiom 2, and we get P of A plus P of B intersect A complement. Now, that's still not yet clear. Why is that the same as this? So here we use another proof strategy that I call wishful thinking. So I wish, I'm going to put a question mark here. It's very, very bad practice to just start writing things you wish as equality without justification, but it's okay if you put a question mark, okay? So I'm going to put a question mark here, P of A plus P of B minus P of A intersect B. I wish this is true, okay? Now, I know this is true, but I'm pretending I don't yet know this, and I want to see whether it's true, okay? So that's my wish. Now I'm going to try to compare this and this. Well, let's see. P of A is the same as P of A. That's okay. So this will be true if and only if this term is the same as this difference. So this is equivalent to, I'll just rewrite that as this equals this minus this, but it's going to be easier to write it without the minus sign, so I'm going to move the P of A intersect B over there. So that's equivalent to saying that P of A intersect B plus P of B intersect A complement equals P of B. I just said, for this to be true, what we want is for this to equal this difference, and then I just move that to the other side of the equation. Okay, now we just have to check, is this true? Well, yes, it is. This is true. It's immediate by axiom 2, because this is true because A intersect B and A complement, and I'll write it this way, A intersect B and A complement intersect B are disjoint. Because if you had an element in both of these sets, it would be in both A and A complement. That's impossible. So they're disjoint, and their union is B. Because what we did was chopped B up into two parts. We split B into two cases. We have the part of B that's in A, and we have the part of B that's not in A. So there's two disjoint cases. Okay, so that's the end of the proof. So this rule is a simple case of what's called inclusion-exclusion. And let's do a more general version of inclusion-exclusion. And then I'll talk a little bit about why it's called that. Then we'll do an example of inclusion-exclusion. Okay? So here's the general inclusion-exclusion formula. It looks ugly, but the idea is pretty simple. So I just want to extend that to the case where we have more than two events. So let's do the case with three of them first. P of A intersect B, A union B union C equals, and we draw another little diagram. Now we have three events, A, B, and C, draw linking rings kind of thing. And I want the probability of the union. Okay, so we're going to start out just like we did there by adding the individual probabilities, and then we're going to adjust for double counting, things like that. So we're going to do P of A plus P of B plus P of C, but it's clear just from thinking about the picture, that we've added too much, right? That we've overcounted stuff. So what we have to do is subtract off the intersections. So we're going to subtract off A intersect B, and we're going to subtract off A intersect C, and we're going to subtract B intersect C. Okay? Well, now we've subtracted too much. If you think of this, think carefully about this picture. What happened to the stuff in the triple intersection? Any stuff in the triple intersection, we added it 3 times, then we subtracted it 3 times. Now we haven't counted it at all. Everything that's not in the triple intersection is correctly accounted for. Stuff that's in the triple intersection we have not counted yet, so we fix that just by adding this back, A intersect B intersect C. Okay, so that's inclusion-exclusion, and you can prove this in a similar way to that. It's more tedious. I'm not going to write out the whole thing. There's also some more clever ways to do it that we might come to another time. It's completely analogous, just a more tedious version of that. And in general, you can use induction, and I'm not going to write out the whole induction because the idea is exactly the same as this idea. The general case, when we have the union of n events, the general form of inclusion-exclusion. If you remember this, then it's really easy to write this down. It looks ugly, but it's the same idea. First, we add up the individual events. Then we subtract the intersections. So I'll just write this: subtract I less than j, p of ai, intersect aj. I wrote I less than j because then we don't have like a1 intersect a2 and a2 intersect a1. We only want to have that once. And then you add the triple, so it's alternating, just like this is plus minus plus. We then have triple intersections. Let's say I less than j less than k, ai intersect aj intersect ak, minus dot dot dot, and then the last term is the intersection of everything. And it's either going to be a plus or a minus. And I think it should be -1 to the n plus 1, because if we think about the case when n is 2, then we stopped by subtracting. In the case n equals 3, we stopped by adding. So it's -1 to the n plus 1, and then the intersection of everything. Okay? So hopefully you can see kind of what the intuition is for this, and why is it called inclusion-exclusion? Because just think of this case with 3 of them. We started by including all of these, but then we've overcounted, so we start excluding stuff, but then we have to adjust the other way, so we start including and excluding, and keep alternating including and excluding, and then it all works out. Okay. Here? This one does not have a summation because there's all n of them. So this is all of them. So there's only one of these. The rest of them will have summations. Okay. So let me do one famous, interesting example of inclusion-exclusion, how you can apply this to a problem. This is a very old problem. It goes back to, what's the guy's name? Montmort's problem. Which was from 17-something. I think 1713. I wrote it down somewhere. 1713, yeah. And this goes by different names in the literature. Sometimes this is called the matching problem. Usually I'll just call it the matching problem, or I'll call it de Mortmont's problem. I don't actually care if you know the name of the problem. I care that you know the concept. It goes by other names because it's a pretty natural problem that comes up in different contexts. Okay, so there are many different ways we could phrase this problem. Different forms of the same thing in different disguises. But I'll tell you the original one. Not surprisingly, this originated from considering a gambling game. De Montmort was interested in a lot of different gambling problems. In 1713, probability was still in its infancy, and he was studying some of these gambling problems, which had real practical consequences for gamblers. There was a lot of money at stake in this. That was the motivation. So here's the problem. Consider the following card game. We have a deck of cards. Now, it's rather than thinking like ace of spades and 7 of clubs, it's simpler to just assume that the cards are labeled 1 through n. So imagine I have a deck of n cards, and each card just has a number from 1 to n on it. Okay, 1 number per card. So we have n cards labeled 1 through n. Here's the problem. So I'll describe the game. And I think they actually played this game back in 1700. Shuffle the cards. Okay. Now, basically, I'm going to flip over cards one at a time, and you're going to count from 1 to n. Okay. So I'll flip over the first card, you say 1. I'll flip over the second card, you say 2. Flip over the third card, you say 3. We'll continue that way. Now, if it ever happens that I flipped over a number and you said that same number, you win. Otherwise, you lose. That's the game. That's why I call it matching, because it's like you win if for example, the 7th card is card numbered 7. That is, the card that's 7th in the deck has the number 7 written on it. Okay? Does everyone understand what the game is? So you want to know what's the probability that will happen, that there will be at least one card whose position in the deck is the same as the number written on the card. All right, so I'm not going to write out that whole description just now, because hopefully you understand what the game is now. So let's find the probability. Well, to find the probability, we need to define some events, right? By the way, you can try, there's more than one way to solve this problem, and you can try to do direct methods, but it's pretty hard to find a way to do this without inclusion-exclusion. Not impossible, but inclusion-exclusion is the easiest way to solve this, I think, and it's also a good example of it. So we need to define our events. So let's say, let's call it AJ be the event that, I'll just say it in words, the event is that card, jth card matches. In other words, the jth card in the deck is numbered as card J, okay? So what we are interested in is the probability of the union. That is just the mathematical expression for the probability that at least one card matches. That's the probability that you win the game by having at least one match. Okay? So it's pretty hard to do directly, but inclusion-exclusion, it looks kind of ugly. So I usually try to find when I'm trying to solve a problem, I usually try to avoid inclusion-exclusion at first. But if I don't think of another method, then I'm going to try this, because it's just a very powerful general technique for finding the probability of a union. Okay? So, well, we need to do inclusion-exclusion, right? So let's just start writing this out. Luckily, in this problem, we have a lot of symmetry, and we should take advantage of symmetry whenever we can. So initially, I would have to write out this sum, but actually, the probability of AJ, well, let's just kind of do some kind of scratch calculations. Do some scratch work over here. P of AJ is the probability that the jth card in the deck is card J. Now, you can do this using the naive definition of probability, because we're assuming there's two ways to think of this. One way would be to have n factorial as the denominator, because we're using a naive definition. We're assuming all permutations of the deck are equally likely. So that'd be fine, but an easier way to think of it is just that it's 1 over n. It's 1 over n because all positions are equally likely. All positions are equally likely for the jth card. I'll say for the card labeled J. Right? So if the card, I'm looking for like the ace of spades, imagine you have 52 cards and I'm looking for the ace of spades is equally likely to be anywhere, so there's a 1 in 52 chance that it's in any specific position. So that's immediately 1 over n. You can also derive this using the naive definition with an n factorial. You'd have n minus 1 factorial over n factorial. You'll get the same thing. Notice this does not depend on j, okay? That's what saves us here. If we had like some complicated thing involving j and n here, then we're going to have to do a summation. But there's no j here, so that means we're just going to multiply this by n. All right, now let's do P of A1 intersect A2. So I'm using symmetry. I could have written AI intersect AJ, where I not equal J, but I may as well, for concreteness, pick 1 and 2. Let's just think about what this is. Here I will do the naive definition. There are n factorial possible permutations of the deck of cards. Now, what does this event say? It says that card number, the card on top of the deck has a 1 on it. The card that's second has a 2 on it. The other n minus 2 cards can be in any order whatsoever. So for the rest of them, it's n minus 2 factorial. And we could either leave it this way, or we could cancel some stuff out and write this as 1 over n minus 1. Because everything else cancels. Okay, and continuing in this way, if we want P of A1 intersect blah, 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 intersect, let's say, AK, well, what that says is that the first K cards are exactly 1 up to K. The remaining n minus K cards can be in any order whatsoever, so the denominator is still n factorial, the numerator is n minus K factorial. All right, so that looks kind of messy. But the nice thing is that we have symmetry, so this will work, you know, whatever choices you put there, okay? So now let's just quickly apply inclusion-exclusion. We start by adding up these ones, and there's n of them, so it's n times 1 over n. Okay? Now we add the next one. How many of these are there? Well, there's n choose 2 of these terms. Except we're subtracting now because we alternate. And there's n choose 2, but I'm going to write n choose 2 as n minus 1 over 2 times that thing, 1 over n minus 1. So it's 1/2. And let's just do one more term, and then you'll get the idea. N choose 3, I can also write it as this way, over n choose 3 is n minus 1, n minus 2 over 3 factorial. I can think of this as 2 factorial if I want. Times, and then whatever this thing is in this case, well, it looks like n minus 1, n minus 2. So you actually see something really nice happens, which is you have n minus 1, n and n cancels, and n minus 1 cancels, n minus 1, everything is basically canceling here. The only thing that's left is these numbers, this minus, you know, dot, dot, dot. So what this then works out to, well, it's going to look like this alternating sum, but I'll just say what it is approximately is 1, well, so it's 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus blah, blah, blah. Well, it's actually equal at this point. Okay, and then the last term is whatever it is, negative 1 to the something over 1 over n factorial. Just get, you know, whatever the pattern is for the last one. Let me make sure I got the last term right. And so, yeah. So this is plus negative 1 to the n, 1 over n factorial. I'm just following the same pattern here. Okay, this looks messy. That's the exact answer. I know we're out of time, but this is the end because this, we can immediately say, oh, this looks familiar. Like, this looks ugly, but it looks familiar, right? This should remind you of the Taylor series for e to the x. So in fact, this is approximately 1 minus 1 over e. We're going to see this number 1 over e a lot in this class. It seems like this problem has nothing to do with e, but here e comes up just because we have this sum. Okay, so have a good weekend.